us go and do some practicals. So in the practical, again, you have a folder called as real-time course material. Wait, I will resume the screen share first. So I hope you can see my screen, and you will see that in the real-time course material folder, I have provided, or do not worry about the repetition, I will definitely do it at the end. So right now let us go for the practical analysis. So you will see that I have also shared a .eds file that will open in the Quant Studio real-time PCR system, right, by Applied Biosystems. So once you open this, I will just show you a few of the differences that how you set up. So initially, if you remember yesterday, that in the standard curve, I have chosen this standard curve method in the machine, right? Maybe I have to start. Okay, so you will see that in the standard curve, you have chosen what type of experiment? Standard curve, right? Whereas in here, since it's a comparative delta-delta CT method, you chose this one. And then similarly, like you have to make a plate that where you in the 394 well plate, 396 well plate, where your sample is, whether it is which gene it is, and then you have to label that what sample it is, whether it is a biological control stress, biological control control sample. So all those things you have to assign, and then you will see that in the setup itself, in the assign, in the define, you will see that there is a column that what in the analysis setting, that what reference sample and what indigenous control you want to choose, based on which the software will do automatic gene expression analysis. But as I said that we should not rely too much into the gene expression data given directly by the software. In the analysis, in the gene expression part, oh wait, just a minute. Okay. So what happens is that in the direct analysis, when you are doing, is my screen visible? Everybody can see my screen? Yes, okay. So I think there is a problem for some people because of their internet issues, which is what's it. So in this particular image, what you can see is that the software itself is telling you that it has calculated the log fold changes, and you can observe that whether the C1, C2, S1, and S2, how much is the difference in the gene expression fold. But as I said, that it is using a formula delta delta CT, it means that it is not taking into consideration your primer efficiency. Let us not do this. Let us not use what the software has directly given us. Instead, we will go in export, and we will click on result and start export. It's the same way what I have shown you yesterday for standard curve. As a result of which, there is another file which I have shared labeled as expression analysis. If you open it, there is a raw data, right? So basically this raw data is coming from the same instrument, I mean from the same export option of the instrument here, right? Once you export, you can make it. So this is a customized data for your learning. Here you have 1, 2, 3, 4, 5, 6 genes, out of which tubulin I am using as a reference gene, which I will show you how you can use it for the analysis. And then you have two conditions, one is control and one is a stress. So triplicate of control and triplicate of a stress. The first method was delta delta CT value, right? It means that it was having a formula of 2 to the power minus delta delta CT, and delta delta CT stands for changes in the CT value of the condition A, that is control, to the stress, right? So this is clear, right? Now, if you find here, the first step is to calculate average. So you calculate the average. If you click on the column average, let me zoom it so that everybody can see easily. Okay, so if you click on this, you will see that what I did is that I made the average for all the genes, for tubulin, for ATP, for RBCL, for PSB, and so on, right? That is the first step. Once you have made an average, this Excel sheet is with you, so you can open simultaneously and either go with me or otherwise you can do like that. So this is the control and the stress value for tubulin, ATP, RBC, PSB, HSP, and GPX, right? So 5 gene plus 1 reference gene, and you have a control data and you have a stress data. Now the first step is what? If you remember from the slide, what was the first step? The first step was to make the delta CT, or to find the delta CT of control and find the delta CT of experiment, right? So here you go. The step is to delta CT, that is control target minus reference gene, and stress target minus reference gene. So you subtract target minus reference gene here for the reference. Similarly, you do for the ATP, right? So why it is 0? Because you are subtracting reference minus reference, right? Because at the end, this is your gene of interest, that is ATP. So 32.909 is the CT value, and that you are subtracting 26.02. So that is giving you delta CT value for ATP. And similarly for RBCL, PSB, HSP, and GPX. Okay. At the same time, delta CT of stress is K4 column. So K4 column is your ATP stress minus tubulin of stress. Okay. Similarly, RBCL L4 minus J4. So RBCL stress minus tubulin stress. Similarly, you do. So basically, in Excel, you have the facility that once you write a formula, you can drag it, copy it. So similarly, you calculate the first step, that is delta CT for control and for stress. Now, when you have the delta CT value for control and for stress, the second step is to find delta delta CT. Now, delta delta CT is what? Delta delta CT is delta CT stress minus delta CT control. So, you go with delta CT stress minus delta CT control, and then you will get a value, right? So basically what you did, you subtracted your delta CT of stress to the delta CT of control, and then you get some values over here, right? Now, finally, once you have the delta delta CT value, this delta delta CT value will go where? It will go, if you remember well, the formula, wait, I will show you the formula. Here, 2 to the power minus delta delta CT. Right? So you will simply put 2. So in Excel, how you will put it? You will put 2 exponent minus of this particular value, because this value is your delta delta CT. So 2 to the power minus delta delta CT will give you a normal expression, I mean normalized expression, right? Now, After you get your normalized expression, in most of the paper you would see that you are representing in the fold change, right? Log fold change. So how would you calculate the log fold change? Is nothing but simply again use the function of Excel, that log, and how would you write it? Log in bracket this normalized expression value, and since you want in the log base 2 fold change, you have to just put a comma and give 2. Once you do that, you will get a result, right? And here I have made a graph for the same data. So what it says is, since one is your tubulin, it is not reflecting because all the analysis has been done in respect to tubulin, right? So you have your ATP, RBCL, PSB, HSP, and GPX. All are showing what fold change you can see from the graph. If anybody is having any questions till now in the delta city, you can ask in the chat. I will try to rectify it. So Aditya,
Yes, yes, I can hear you.
yeah, so it's audible, right? There is no internet issues at the moment.
No, no, it's all right.
Okay, okay. So log fold change is a way how you represent your difference in the expression values. So basically, when you are calculating the normalized expression, the normalized expression, relative expression, can be found 2 to the power minus delta ct. So 2 represent your fold change. So whatever result comes, that's your relative normalized expression. And in order to make it uniform in the log fold, you represent it as log base 2 fold change. So relative expression and fold chain are just a way of expressing things. Why we are saying relative expression? Because if you would be observing here that you have two conditions, control and the experiment, right? Control and the stress. But in the bar graph, you will see only one particular column, I mean for each gene. So it means that whatever you have analyzed or whatever you have found, it's the expression of the gene in the stress condition in comparison or in relation to the control condition. So that is the relative gene expression, right? So that is why you can call it as relative expression. And in order to express it, you convert it into the log fold change. So log base 2 fold change, that is, you just have to convert it into log base 2, or you, if you want, you can leave it in linear, but I mean in the normalized expression, but you need to specify in your publication or wherever you are using the image that this is not a log fold change, or simply that the graph represents the normalized expression value. Okay, so this is one thing. So I hope that is clear now, right? So we will go in the second one, which is more correct, or you can also say because it has taken into account the primary efficiency. Now the same data set here, I will just maximize it in the center and minimize this one. Okay. So now I hope it is clearly visible. So it is the same data set what you have for delta city. So in the same data set, you will see that how the efficiency, primary efficiency, will affect the expression values. So again, to make the things more clear and to make you more aware, I have made a step-by-step calculation in the same Excel sheet which you have been provided. In that you will see that you have, first step is to find the primary efficiency. Well, we have already done it in the, I mean before half an hour. You already have a standard curve calculation. So basically, just to repeat it, you have the gene, you have the cDNA, you convert the cDNA concentration into percentage, make a log of I mean convert into log of the cDNA concentration, create a slope, I mean graph, and then with the help of slope value, you can find the efficiency. So, so this is just in order to make you understand that first step is to make a primer efficiency calculation. Once you have a primer efficiency calculation, what you do is that I wrote here, if you can see carefully, then you will see that for my tubulin, the primer efficiency is 1.99, for ATP it's 1.95, for RBCL it's perfect 2, for PSPA it's 1.191, for HSP it's 2, and GPX it is 1.99, right? Right? So this is how you write the primer efficiency. Now, the next step is to take the average of the replicate. So it is the same step what you did for the delta density, where you have calculated the average of the expression of control and expression of stress. Now here comes the difference in the step 3. Okay, so what happens in that step 3? You
Amit, I can interrupt slightly. Sorry for interruption.
yeah,
Please, if you can maximize your window, that will be convenient for people.
is it okay?
So you can just maximize on full screen. It is coming on half of the screen midway.
Huh. For me,
I
it's
don't know
coming.
why.
So, let me check.
Yeah, now it's fine. Okay, please go on.
Fine. Okay. Oh, internet connection is unstable. Okay, let me do it little bit quickly. Is it okay, Aditya?
Yes, it is fine, Amit. Please carry
Yeah,
on.
yeah. So after the second step, that is the same to your delta city value that you have found your average of the replicate. You have to select a calibrator that you can choose your control, right? So basically, what happens in the formula, if you look, it tells you to efficiency of target and then delta CT, that is mean minus, I mean control minus sample. So what I did is that in step 3, I just copied the value of the average of control over here just to make it a step by step analysis, right? You can see it's the same value, 26.02, 26.02, 32, 32, and so on, right? So this will act as a calibrator or the reference sample for us. Now, the fourth step is that you calculate delta CT. Now, what this delta CT means? Delta CT means here in this particular Poffel method is control average, that is your calibrator, minus stress average. So basically, what you did is you took your J24. So you have uh, this calibrator reference sample here 26.02, you subtracted the stress value of this the stress CT value with the control CT value, right? And you got some value, that is your delta CT. So this particular delta CT for the reference will be used where? It will be used in your, I will show you where you can use it. So similarly for the ATP again, you subtracted your stress from the control. Similarly for RBCL, PSB, HSP, and GPX, right? So that is the fourth step where you are finding your delta CT, and that is your control average minus stress average. And control average is what? The control average is the control CT, I mean CT value average of the control sample, and stress CT value, the average of the stress CT value you are subtracting from the control CT value, right? And then you will get delta CT. Now, what is the next step? Put everything, whatever we have done till now, till step 4, put in the Poffel equation. So, what is the Poffel equation? You can see the Poffel equation is efficiency of target to the power delta CT and efficiency of reference to the power delta CT of reference, and then delta CT of the target in the numerator. So we have divided further into two steps so that it makes easy for you to understand. In the first step, you will find that for the tubulin, which is also a reference gene for me, 1.99, if you see in the formula bar, 1.99 is the efficiency of the primer, and to the power J1, that is your delta CT. So this is the first step to calculate for each and every gene. Now, once you have You can also do both in the one step, but just in order to make it more clear, I have divided into two steps. First is that you calculate just the E epsilon delta Ct. So basically, what you are going to use for the ratio. So 1.99, which is the primer efficiency for tubulin, to the power J41, that is your delta Ct. Similarly, if you see here 1.95 and primer efficiency, where will you get? I have already mentioned here in this particular column, right? Okay, so similarly for ATP 1.95 to the power K1, that is your delta Ct value, right? Similarly for RBCL, PSP, HSP. So what you actually got is you got the efficiency to the power delta Ct. Now in the second step, if you remember well the equation, what it is here in the center of my slide, that is ratio is equals to efficiency of gene of interest, that is your ATP, RBCL, PSB, HSP, and GPX, to the power delta Ct, which you have already calculated over here, and then that is divided by efficiency of your reference to the power delta Ct. Now efficiency of the reference to the power delta Ct is what? It's your this value which you have calculated for tubulin. So in this second step, if you see what you did is that whatever efficiency has came, the e to the power delta Ct has came for ATP, you divided it with the efficiency to the power Ct of reference, that is your tubulin, and whatever it comes will give you again a relative expression. Now the same relative expression you can convert in the log form by the same formula, that is log and then your Ct expression value comma 2. How much is the difference? Let us copy the delta Ct. It's the same data set. Okay, so what I did is that I copied this one, which is in the red color. It's actually from the purple method, and this white one, it's from the delta CTCT method. You will see that it is not drastically changed. Slight variations are there in some of the genes where the efficiency is more or less similar. Now, I will make things more clear. If you go here and if you copy this primer efficiency and you paste it here, okay. Now what you will see is if the primer efficiency was 1.99, then the log fold change from the delta CTCT and the Puffer method is not drastically different. It is different in point O values, like 2 after point, the second value is different, right? So here also there is not much variation. However, if you see somewhere, so basically, in this particular example, you don't see much variations. So this goes here. So you won't see much variations because most of the primer is having more than 90% variations, right? 90% efficiency. In case if it is 2, you will see that it is almost similar, 2.28, 2.28. In case of 2, you will see 2.20, 2.20. In case of 1.91, you will see the fold change in 2.18 and 2.03. Another important thing to notice is that when you are using the log fold change from the delta Ct value, if you have not taken into consideration the primal efficiency, you are actually reporting a little bit higher expression value for the gene. For example, in this case, which is PSP, if you are not taking into consideration 1.99, you are reporting 2.18 relative expression, right? Whereas actually it is 2.03. Similarly, when you have an ATP 1.95, primer efficiency. With the delta delta city, you are reporting 1.87, whereas actually it is 1.80. So now I think you are able to differentiate that what is the importance of the primer efficiency and why you need to take care of the efficiency, primer efficiency and specificity. In this particular example, even though most of them are varying from 91 to 99 or 91 to 100%, suppose if it is not 1.99, let us try doing this. Instead of 1.99, let us make it to 1.65. And now you see, if you are if you have observed here, what has happened from 2.03, it has came down to 1.54, and that is why, because you simply subtracted or you simply reduced the primary efficiency from 1.99, which was previously written, to 1.65. So now I hope it is clear that why it is important to have the primary efficiency corrected, right? So these are the two methods. Now, one more and the last point which I would like to share. Already you have all these calculations with you. One last point which I'd like to share, that I have also shared one file which is called as REST MSC Beta August 2018, right? This is a tool which was generated, I mean, which was developed by the group of Puffle itself. So the scientist who has given us the Puffle method is involved in the development of this particular tool, which is an Excel-based tool, freely available. You can just go in the GeneQuant website and then you can download it. But I have already given you in your folder. See, nothing you have to do. You just have to provide your reference gene, your list of gene over here. You have to choose the condition. So suppose in this case I have just given control and stress, right? So I have just given you control and stress. But suppose if you have stress 1, stress 2, stress 3. For example, if you have temperature of stress 30, 32, 34, 36, 38. So little bit complicated experiment. So you can put your data over here, I mean conditions over here. In the second option, not in the second option, in the third option, you can put your CT value for the reference for the condition 1 here, condition 2 here, and as you go down you will see that there are different condition 2, 3, 4, 5. So at a time you can do for 10 genes, I mean sorry, 10 replicates, and for 9 genes. And in that 9 gene and 1 reference gene and 10 replicates. So after that, once you run this tool, you will get a expression value which you can compare with the result what we have. You can see here. So you can see here that whatever we have calculated, it is same 1.80, 1.80, 2.28, 2.28. In addition to it, it has given you a standard deviation also. Why? Because this particular Excel, I mean this particular tool is taking into consideration randomization. So it is having its own formula of randomization which takes, I mean, different set of data. Here is the formula for that, which you can go through it. And you will see that by changing the different combinations of the replicates what you are providing, it is also giving you standard deviation. However, in case if you want to get the standard deviation and standard error data, instead of making it average for 3, you can also go one by one. So 1 to this one, second to this one, and third to this one. And at the end, whatever average come for 3 of the 4 change, you can report it as delta, as a standard deviation. This is one thing. Second thing is that here you have only 3 stress and 3 control and 3 stress, which could be which I have just given you for the simply understanding the concept. It can be just technical triplicate. So similar to this, you have to have biological replicate three. So in total, you can have nine data. So three from control one, three from control two, three from control three. Do the independent analysis and find out the standard deviation or the standard error, and then you can report it into your publication. So I guess that this is all about what I wanted to explain for the relative gene expression.